Okay, so I'm Kevin McQuiggin, V7ZD KN7Q, and tonight I'm going to spend about an hour or so talking about GNU radio, but also talk about amateur radio, innovation, and GNU radio, because the three topics are related. Amateur radio's role in innovation, and then I want to talk briefly about two classifications of amateur radio operators: technologists and communicators. And that is related to, we'll talk about that, and then we'll actually get into GNU radio and give some, spend the bulk of our presentation talking about GNU radio and related topics of signal processing. And so I think everybody knows that amateur radio has a strong history of innovation in radio systems and operating procedures and that kind of thing. And the hobby, of course, draws people. One of the cool things about amateur radio is it draws people from all walks of life. It isn't that narrow engineer, scientist type of recruit type, the type of people that become involved in amateur radio. They come from all different walks of life, and so they different social backgrounds, cultural backgrounds, scientific backgrounds. Some don't, and everything. And so this is really over the last 120 years been amateur radio's strength, because hams don't have technical bias, they don't have scientific bias, and so they don't know what won't work. And so amateur radio operators very often, and historically, right, they have tried different modes and different ways of setting up antennas and stations and different circuits and that kind of thing. And that has resulted in some really significant discoveries in the history of radio technology. And here we won't dwell on this, but there are a number of different areas like propagation theory, single sideband modulation, microsatellites, and weak signal communications are two of the two or three, I guess 3 or 4 of the different areas in which amateurs have made significant contribution over the last 100 years or so. And so I want to talk about different classifications next of operators, that is technologists and communicators. There's a balance within and we're talking about the people within the amateur radio ranks right now. Most of us can classify ourselves as either a communicator or a technologist. And it's interesting observation is that over the last few decades, the balance between technologists and communicators has significantly changed. And so, so that affects amateur radio's ability to innovate, especially on the technical side. And so we're going to talk about GNU radio for the bulk of the presentation. And so in terms of restoring that balance or changing the balance between technologists and communicators, GNU radio can really help modernize training and enhancing the skill set of amateur radio operators, so that hams can continue to make technological innovation within the hobby. And so this is a historic slide, and I don't have any specific numbers for this. This is just from personal experience, and so I can't quantify these percentages or anything. But if you look at radio and radio technology and innovation within radio technology, if you go back to the mid-20th century, say the 1950s, 1960s, 1970s, on the left, you can see that the orange portion of the pie, those are the technological innovations coming from amateur radio. It was a significant percentage, about, and my estimate would be, knowing something about the history of the hobby, probably about 25% of the innovation and new ideas for circuits and antennas and that kind of thing had an amateur radio background. Now, fast forward onto the right-hand side, into the 21st century, notice how the percentage of innovations coming from amateur radio has just become a sliver, right? It's been overtaken by industry innovation coming from industry, academia, and from other sources. And so that is not good. I mean, it's good that people are innovating, but as far as amateur radio is concerned, the fact that the percentage of innovations that are coming from within our hobby is shrinking and shrinking and shrinking, and now is just a sliver of what it used to be. I think that that is not good, because one of the foundations, one of the bases of amateur radio is one of the reasons amateur radio exists is because government and even industry said, hey, amateur radio can contribute to the radio art. They can contribute to radio science and everything. And why is that? That's because hams come from a broad-based segment of society that they don't know what won't work, right? Going back to the first couple of slides. And so I think industry and government and everything, they valued that not knowing what won't work as a source of creativity, source of change, source of innovation that traditionally for many decades came from within the ranks of amateur radio. And so the last 50 years, the last 50 years or so, we've seen this great reduction in the contribution in technological innovation by amateur radio operators. Now, I talked before about technologists and communicators. We should define what they are. And so look at yourself as an amateur radio operator. You can say, am I a technologist or am I a communicator? Well, here's a bit of a definition. Technologists focus on their interest in the hobby. Their focus in the hobby is the technology and the radio science. They like designing equipment, building equipment, experimenting with new modes. And especially in the modern times, they like writing software, writing digital radio software, for example, right? Technologists, they like finding answers to fundamental questions, things like how does radio work? How does propagation work? Why does this antenna work better than another one? If I build an antenna that is shaped like this, is it going to work better than one that I had before? And so they focus on the technology and the radio side of the hobby. They're a different group, right? There's a distinction between technologists and communicators. Communicators, they're the other group of hams, right? The other, and really, there's no hard division between this. People can be a technologist and a communicator and that kind of thing. But generally, if you find yourself as a communicator, you have less interest in radio than your interest is not in radio and how it works and the technology. You're interested in how can radio be used to communicate? How can radio be used to support emergencies, support community events, to improve service, to improve service or improve the use of radio, the capability of radio, and its ability to help others, right? And I would say even if you're a DXer, right? You're a DXer. You have you're going to have some technological background, technological understanding. But if you're a big DXer, big contester, you're really a communicator because you want to use radio. How can radio be used to communicate, right? And everything. So if we look at the percentage of technologists versus communicators going back to say around 1980 or so in 2023, one of the things that we've also seen, as well as this change in the amateur radio innovation, is that going back to about 1980 and before, the percent technologists were outpaced, or there were way more technologists than there were communicators. The two divisions still existed, but the technologists dominated. And between 1980 and 2023, that has been reversed, right? The technologists, in fact, have gotten, the percentages have been swapped, and that percentage of technologists has gotten even thinner than it was back than the communicators were in 1980. And so we've seen a move in that. What this means, I guess, in English is that we've seen a move towards the social, or move towards the operational focus of amateur radio, and away from a focus on technology and everything. And that also affects amateur radio's ability to innovate, the ability to contribute to radio science, contribute to industry, contribute to academia with new ideas for circuits and antennas and that kind of thing. And so what are the consequences of this? Yeah, and this documents, I guess, just what I said. The technological focus has receded from what it was up until about the 1980s. And that isn't to say that amateurs aren't curious, they aren't innovative and everything, but that spirit still exists, right? And there's still that power of that power of amateur radio, because people coming from all walks of life for creativity and that kind of thing. But in the current time, because of the dominance of communicators, the technical foundation to fully understand modern technologies, and now I'm folding back into GNU radio and digital signal processing and software-defined radio and everything, with the focus on communication rather than technology within amateur radio, the technical foundation to really understand how these new technologies work is lower than it was before, because most hams, whereas most hams used to be technical and have technical interest in radio and electronics, they don't anymore. And so that is a further challenge to amateur radio, a further challenge to the ability of amateur radio to contribute, because of this lack of technical foundations in order to understand, especially modern technology. And so the effective reversal of motivation left the hobby far less capable to innovate and develop new technologies, new techniques. And so, hey, what's my opinion about this? I guess I've been stating my opinion, but just to summarize, I think that amateur radio still has contributions to make to the radio art. Amateur radio is still it's a good place to innovate. It's a good place to experiment. It's a good place to come up with ideas that can be folded back into industry and into the radio art as a whole. And when we see this in society, this is more a comment on society. Society increasingly is trying to rely on commercial infrastructure for communication in time of an emergency, right? If there's a disaster emergency, they're saying, well, we'll use Twitter, we'll use our cell phones, we'll use Facebook, that kind of thing. And the problem with that, as everybody knows, I think everybody at the meeting will know, right? All these commercial technologies, they depend on billions of dollars of commercial infrastructure. Amateur radio is able to bypass that, right? It's able to bypass that, provide communication when all else fails and everything. But the trend, because amateur radio is getting less technical and is contributing fewer innovations, the trend in society is to not pay attention or forget about amateur radio because of the changes that have taken place over the last 20 or 30 years within the hobby. And so there should be some effort to return to a more technical focus for amateur radio. And I'm not saying that tests need to be harder and people have to write circuit, they have to know Morse code, they have to do this, have to do that. That's not what I'm saying at all. But I think it would be really, really good for government, really, really good for the amateur radio service to try to get a little bit more technical, to try to reverse this loss of technical knowledge. But that is difficult. That is difficult because of that's difficult, of course, because of the increasing complexity of the technology, and especially digital radio, software-defined radios, digital signal processing, that kind of thing, because they're not simple concepts. But GNU radio can help, right? GNU radio can help, and that's what this talk is all about for the most part, right? If we do these things, we'll build a more capable amateur radio service. And so in the background here, we're going to talk about this. This is a GNU radio flow graph. And now you do pronounce the G with GNU radio, right? It's I suppose it could be new radio, and in terms of the animal and that kind of thing. It'd be new radio, but the tradition, the definition of the project, and it's GNU radio. So you do pronounce the G at the start of the name. What is GNU Radio? We're going to spend the most of our time talking about that now. It's a free open source cross-platform application that runs on Windows, runs Mac OS, and runs on Linux. And so it is a program, an application that you download from the GNU Radio site that you install and run on your computer. It has a GUI, and what it allows you to create radio systems which are built from combinations of standard blocks. And so GNU Radio uses a block model. It has about 200 different blocks. These blocks perform functions. We're going to see some of them in a couple of minutes. But because it has a graphic user interface, you drag these blocks to the desktop and you connect them, right? You connect, each block has input and multiple inputs, one input or one output, or one input and two outputs, or multiple inputs, multiple outputs. And you use the graphic tool, use the desktop to connect the blocks together in various ways. And they're standard blocks. They're things like, as we're going to see, you could have a microphone and a speaker and a filter and a modulator and a demodulator, that kind of thing. You drag these to the desktop, you hook them up, and you build your own radio system at the block level. And so it's very, very cool, very, very cool in that regard, and it makes building radio systems sort of intuitive. Now there is sort of intuitive. So GNU Radio focuses on radio systems at the block diagram level. And so you're not building circuits, you're not dragging diodes and transistors and resistors and that kind of thing, because everything operates in this model of blocks. And so you select GNU Radio blocks and you connect them together into what are called flow graphs. The flow graph is on the desktop, right? And then as soon as the flow graph is complete, you're able to run the flow graph. when you say run, GNU Radio translates the flow graph to a computer program that happens to be written in the very popular programming language called Python, and runs it. And in conjunction with hardware, like a receiving module, it's called an RTL dongle, or several different types of digital radios. And so in conjunction with this hardware device that you connect to your computer, usually through the USB port, you connect the hardware, because you're gonna have to have hardware if you're going to build, for example, a radio receiver. You connect the hardware, the RTL radio, to your USB port. You load your flow graph, you run the flow graph, and then you have a functional radio, and it's all done in software. It's very, very cool. And so I want to say, as I start out, we before we talk about anything else, is that GNU Radio does have a learning curve, right? It the package presumes that the user understands the fundamentals of radio. And I would say all of us as amateur radio operators, we understand the fundamentals of radio, and to just about a sufficient level to be able to understand the different blocks within GNU Radio, right? And so you may have to brush up on some of the details and that kind of thing. We understand the radio part. What we don't understand as hams is the digital signal processing. And so that is where you have to, in order to use GNU Radio effectively, that's where you have to do some reading, you have to do some study, if you are a new user to this. We have half the job done as amateur radio operators, because we understand the fundamentals of radio: transmission, reception, modulation, demodulation, filtering, all that kind of thing. We understand, we have an intuitive concept from our certifications what these blocks do, or what these functions do. And so the only thing we have to add to that is an understanding of digital radio. Digital radio has components in it, like things like sampling rates and things like filter taps, and there are a bunch of things that you can learn as you go, right? And so that is where you probably, if you want to get really, really into it, you're going to have to do some extensive reading. But otherwise, you just have to do a little bit of reading and do some tutorials, look at some examples, some YouTube videos and everything, in order to get started in this fantastic area, right? And so there are tutorials, they're excellent background material, and I have some references coming up at the end. And I would summarize this learning curve by saying GNU Radio has 200 blocks. You have to have a knowledge of what each of the blocks does. What does this block do? But how the block does it is not really critical, right? If you have a clock recovery, or you have a low pass filter, right? Let's say there's a low pass filter. We all know, because we all know what a low pass filter is. How the block does it doesn't really matter. It does it mathematically, as we're going to see. It does what the block does, low pass filtering of a radio signal. That's usually just about all that you have to know. And so tutorials within GNU Radio, they have an extensive set. We won't go through these, of course. I just wanted to get a screenshot of the web page, but everything from beginner to intermediate and advanced tutorials to how to do basic things within GNU Radio. And even outside of the GNU Radio site, there are lots of resources that you can use as well. So here's some sample blocks for a few slides, right? They have these samples here. They're audio and wave file sources and sinks. The concept in GNU Radio, if something is a source, it's something that provides input into a radio system. For example, you could have a digital receiver. That's the digital receiver. That would be a source, right? It's called an RTL source. I forget what RTL stands for, but it's a digital radio. But you can also have a microphone. A microphone is an audio source. An audio sink is a speaker, right? It's something that you send samples to, and the samples come out in the speaker. And so if you're building a radio, SSB, FM receiver, SSB transceiver, something like that, you'll have an audio source, your microphone, you're going to have an audio sink, ultimately the speaker. You can also use sources and sinks. You can use wave files, audio files. This is really, really handy for testing. And so you can have wave file source, wave file sink. You notice there's a blank in the block. You double click on these blocks, right? Double click on these blocks, and then you get to fill in where it says file name, and that kind of thing. And sample rate is something that we'll talk about a little bit later. Here's some modulators and demodulators from GNU Radio. The first one's an AM demodulator. to its right is an FM demodulator. The bottom two, the bottom left and right, are phase shift keying, PSK modulator and demodulator. And so, undoubtedly, you can use GNU radio in SSB, AM, FM voice modes, but there is so much power, so much of interest within these digital modes like BPSK and QPSK and different digital modes that you will shortly find that man, oh man, you're going to want to get involved in these digital modes, because they support things like RTTY, they will support things like CW, will support things like FT8, FT8 and the modern digital modes and everything. But the idea is that these things, these things are divided into blocks. What happens in an AM demodulator, an FM demodulator, you don't really have to know. All you know is you have to provide, see in red, the channel rate and the audio decimation. And those are the things. Remember I said there's some stuff you have to go and read about. What's a channel rate? What's audio decimation, right? And that's basically the number of samples per second, right? The channel rate and the audio decimation is, okay, are you going to live with that sample rate, or are you going to decimate it down? You probably want to decimate it down to 48, for example, AM demodulator, 48K bits per second. And this is the kind of thing this is where you do some reading, do a little bit of study, and you understand what these things are, because you're going to have to fill them in. Here's some receivers, right? One's called, very, very popular. I have a picture coming up. It's called an RTL SDR source. This is a little $20, $30 dongle that goes into your USB port that provides radio reception capability from about, I think, as they come out of the box, about 2 megahertz to, I think, 3 gigahertz or something like that, right? See, in the red, it says channel 0 frequency. Okay, you can put in 146.94 megahertz, okay? And then you're going to be receiving on V7 RPT, right? What is the RF gain? These other things like IQ balance mode and gain mode and that kind of thing. Don't worry about them. They have defaults. Usually the defaults are fine. The bottom one is a different kind of receiver, right? It's a receiver. It's called a USRP. A USRP is actually a transceiver. So you can use it to send, or you can use it to receive signals, but you can also use it to transmit signals. And that is something that you probably will want to try after you have used the desktop and built a couple of receivers. Build a few receivers. You say, hey, this is really cool. I'd love to be able to generate an FM signal on the 70 centimeter band so I can talk on the local repeater. Then you're going to need rather than an RTL SDR, that's a receive only device. That's why it's $20, right? You're going to need to spend $100, $200 on a more capable digital radio that can also transmit. And hey, I should also say, if there are any questions, please ask. I don't have access to the chat or anything right now, but please either hold the questions, document the questions. We'll come back to them, but don't let me go on if I'm being totally boring or totally ununderstand. If I'm not being clear or anything like that. So here are three examples of filter blocks: a bandpass filter, low pass filter, high pass filter. To us as hams, that their functions are the functions are self-explanatory, right? We need a low pass filter, want a high pass filter, you want to have a band pass. You provide, for example, on the left, the low cutoff frequency, the high cutoff frequency, and the transition width. That is how square do you want the sides of that filter to be, right? And the other thing I'll say is, when you're hooking these blocks together, if you make a mistake, it's only software, right? What'll happen is you're not going to break anything. The radio won't work. Your receiver won't work, and you'll be scratching your head. You'll scratch oh, why doesn't my receiver work? Oh, maybe my transition width was too broad, or maybe my low cutoff frequency was wrong. So you just go back to the flow graph, double click on the block, you edit it, try it, and run it again, right? It's not like you're building things, that you're soldering stuff together that doesn't work. You're just fiddling with software, and you can try and try and try and try, and eventually you find the combination that works, and then you've learned. The other thing about the blocks is here's the digital presentation is way more understandable to new hams. Which is more understandable if you're working towards your basic certification? Oh, here on the left, low pass filter schematic, right? And this is from some training material. Coil 1, coil 2, coil 3 is 178.9 nanohenries, and it needs a Teflon capacitor of 74.1 picofarads. Okay, well, you can sort of get the idea. You can look at that, and the important thing for the new ham is, oh yeah, those are tuned circuits. But isn't it really more understandable on the right? Low pass filter, cutoff frequency 60 kilohertz, transition width 2 kilohertz, right? And so this is where digital radio can actually be simpler, right? Could actually be simpler for new hams, simpler for people starting out in the hobby than the old way could. The challenge that we won't get into in this presentation is that government sets the exams, their international standards. It'd be very, very difficult to take amateur certifications and just wholesale move them over to digital processing, right? Because regulations would have to be changed, standards would have to be changed. It'd be a very, very long process. But I would say, but I want everybody to see conceptually, hey, on the right, low pass filter, it's way more clearly represented. The idea is way more clearly represented than probably than the stuff on the left. I should say on all these blocks, look at the little blue tabs on there. And if I go back to previous ones, see they have little blue tabs. The tabs can be different colors. The different colors depend on, okay, what kind of numbers, because everything's digital, what kind of numbers go in, what kind of numbers come out. But those tabs represent input and output of the blocks. Like look at the RTL SDR source. That's a receiver, it only has output. Because if you're receiving stuff, you receive signals off the air, they get digitized, and the output goes into the rest of your flow graph. But that's what the little tabs mean on there. Now, here's another example. This is, I think thanks to John Schutten, I think this is from a recent, the basic certification course. It's a diagram, a block diagram of a CW and SSB receiver. We've all covered this. We all understand what's the mixer, the radio frequency amplifier, the mixer, the filter, the IF amplifier, all that sort of stuff, the audio frequency. We understand what these all blocks are. But this is a great way to learn. This is a great way to learn conceptually, how does a radio system work? Here's a FM receiver for the broadcast band in GNU radio, right? And look how similar it is, right? The details are the details are different, right? There isn't a block called high frequency oscillator or anything, but the idea of this flow through blocks is very, very similar. The front end of the radio, the radio frequency amplifier, the antenna and everything, that's RTL SDR. There's we have mixer and filter. The mixer and filter are handled by the low pass filter. The filters in red, see it says filters the AM signal. The demodulator is a block called wideband FM receive. It has an input. So the signal comes in from the RTL SDR, goes into the low pass filter, out of the low pass filter, into the receiver. Out of the receiver comes audio, right? And it goes into a multiply block, because you have to think everything is in numbers. And so numbers come out, and then the volume control is you just take the numbers, take that stream of numbers, and you multiply them by 10 if you want it really loud. You multiply it by 2, multiply the number stream by 2 if you want it to be really really quiet, right? So that's why volume control is a multiply block. And then then the numbers go into the audio sync. We spoke about syncs right at the start. The sync is something that goes to the speaker, right? So the numbers are, so signal is received and the signal is demodulated, goes through the volume control, goes to the speaker, and then you get audio output. The other blocks down at the bottom, they are things that define the sample rate. The sample rate indicates how often are you going to sample signals that are coming off the air. And then the sliders, three sliders, right? One for frequency. You want to set the frequency of your radio, little slider on the screen that you can drag back and forth. You can set RF gain, and then you can also set volume. And so very, very similar. Eh? It's a good way to represent a radio. Here's an SSB receiver, single sideband receiver for GNU radio. It's upper sideband, lower sideband. It's a similar sort of thing. This one is using an USRP rather than an RTL dongle. But I could just as well have dragged an RTL dongle or an RTL SDR receiver block there. There's no real difference. And so frequency translating filter that selects a portion of the signal. It takes the complex signal, converts it into a couple of floats. And this is where, on the digital side, this is where you have to do that reading to understand, okay, how is a signal, we're going to talk about that briefly. How is a signal going to be represented? Because signals are represented in digital radio by numbers. And so see the two multiply blocks? You take the complex, you multiplying things, multiplying a signal is like mixing signals together. If you have a mixer, you take two number streams, you multiply them together, and that on the digital realm, that's like creating a mixer, right? And so the so we won't get into the details of how the flow graph works, but on the right hand side, we get on the right hand side we have an adder that adds the two components for the two components together in order to select, and then the multiply constant -1 selects upper sideband, lower sideband. The multiply constant in the top right is a volume control, and then it changes the sampling rate to match the audio sync. And 48 kilohertz, if you have a computer, right, the choices are 44.1 kilohertz or 48 kilohertz generally on a computer. The idea here is not to get into this in detail or not to scare anybody. Oh, I'll never understand this, because on the contrary, you can easily understand it if you make a little bit of effort. And so, but notice, similar to this SSB receiver block diagram, the key takeaway from this is that, hey, you just drag these blocks, connect them together in the proper order, and you have a radio. And so this model scales. It makes it. This model scales. You can make much more complex things by understanding how these blocks work and dragging them and connecting them together. So I have three examples, go through really quickly. One is a 1500 megahertz receiver for monitoring satellite telemetry from the Inmarsat series of satellites. The second example is a subcarrier audio signal that is carried on local FM broadcast stations. We'll talk about that a little bit. And the last one is a QPSK digital transmitter, right? It'll transmit digital signals anywhere from 70 megahertz to 6 gigahertz. And so Inmarsat, and this is the Inmarsat, go to 1545 megahertz. This is the spectrum, right? If you had a spectrum analyzer, you look at the signal coming off of the Inmarsat satellites in 1545 megahertz. You see they have a number of voice and data channels, and then the voice and data channels, the peaks and everything. There's a noise floor, and then look right in the middle. There's a control channel, right, that has telemetry at 600 bits per second. So I thought this was really, really interesting, and in fact, what I did is I used GNU Radio to write a program that will decode the telemetry channel, or decode the control channel. And so that was subject of an earlier presentation, and did that a couple of years ago and everything. But the key for this presentation is that you can write a flow graph. You can write a flow graph that allows that to extract that information. The secondary audio channel, for some reason, it's called SAC. It's called SCA instead of secondary audio channel. You think it would be called SAC, but specifications as they are, they call it SCA, and on FM broadcast stations. This is the spectrum, 150 kilohertz wide of an FM station. You can see the main signal down at 0 kilohertz. A pilot tone. The pilot tone is there at 19 kilohertz. That indicates whether whether the signal's stereo or not. Then the stereo content, the second channel is provided around 35, just under 40 kilohertz. Above that, around 53 kilohertz. See, it's called RDS data. That's all the stuff that you see in the car if you have a fancy receiver at home. It says country and western. This is Shania Twain, and it gives the song title and that kind of thing, and information about the station. That's all carried in the RDS data. You can actually decode that using GNU Radio, using a fairly straightforward flow graph. And right up at the top, just under 100, there's actually a number of FM stations on 93.7, the Vancouver area. They actually have a secondary audio channel on that FM signal. You don't hear that because all you're interested in with the broadcast receiver is the main signal and the stereo. Maybe the RDS. The RDS will be decoded if your radio can do it, but the secondary channel is not generally accessible. It's not accessible for a normal receiver. You buy a specialized radio to do it, or you can use a flow graph. So with GNU Radio, you can easily decode all this stuff, right? You need some documentation about the modulation and everything, but you'll come up with a a more complex flow graph. We won't talk about it, but it's just a little bit more complex, and that extracts the control channel and sends it out to where it can be printed. Here's a transmitter for secondary audio channel. Again, it's it's a number of blocks. Connect them together. Once you understand what you have to do, you connect them together, and you can actually. And I actually did this within my shack, right? I had audio on the main channel in stereo, and then I had a secondary. I used a second wave file to transmit audio in the secondary audio channel, and I actually can receive it. So very cool. And if you wanted to build a digital transmitter, they're actually really, really straightforward. All the blocks that have purple handles and purple inputs and outputs, they all deal with bytes. They all deal with bytes and data. And what this transmitter does is it just reads a file and transmits it over and over and over and over, and it goes into what's called an SDR sync. See, it's called Pluto SDR sync. Pluto, you'll see one in a second. It's a fairly affordable $100 transceiver for digital radio. And so the bytes are processed, they go out there, and I have QPSK transport. So these complex projects are possible. So if you want to build a general coverage receiver, RTTY, packet radio system, cell site emulator, Doppler radar, any sort of thing, you can do that with GNU radio. And I have the footnote that says, would you like to build a, well, you're going to write that. You're going to create a flow graph that gets translated to a Python program. So what you have to do is you have to believe in your ability to learn, because as they say, right, as the saying goes, every journey begins with a single step. So what you need to do is just invest some time reading and thinking. You have half of the prerequisites already as an amateur radio operator, because you understand radios and radio technology, how radios work, the different components. You just have to learn the digital side. And so invest some time reading, thinking. I have references for you. You can install GNU radio, and then plan to experiment. Have a plan. I'm going to experiment, and I'm going to fail a lot. I failed hundreds and hundreds of times before I understood how this, and honestly, I still don't fully understand it. And so we're going to go on. Talk about digital radio short overview. And I think I'm doing all right for time. So I hope that's good. Okay. So digital radio is mathematical. It's looking at radio from a mathematical perspective. You do not have to be a mathematician. You don't have to understand calculus. You don't have to understand complex math. Remember I said right at the start that these blocks do things? You have to understand what the block does. You don't have to know how the block does it. You have to know very little about how the block does it, right? And so radio signals have corresponding mathematical description. Even in the basic course, they talks about, James Maxwell and Oliver Heaviside, the people that defined the mathematics of radio, right? And so things like AM, FM, single sideband, phase shift keying, FT8, all these things, all these signals, every type of radio signal has a mathematical formula, mathematical description that defines it precisely. Okay, so digital radio processes signals using their mathematical representation, not what we're used to. Now let's talk about analog radio. Analog radio approximates the math. If we have an analog radio, we take inductors and we take capacitors and we take transistors and we build a little radio receiver. We build a little radio transmitter. The thing will work, but now because we're getting into the science, the technology is well advanced. These equations of radio, this mathematics of radio, it's been understood for 150 years, at least 150, even go back to almost 200 years. The math has been understood, but we couldn't do the math because computers didn't exist. Powerful computers didn't exist to do this math. And so second best is that radios were built up until about the 1980s using analog components. Okay, what you have to understand about that, though, is analog radio uses discrete components to represent the math behind radio transmitters, radio receivers. All the analog components do is they approximate the mathematics, right? The mathematics defines FM reception, FM transmission absolutely precisely. But when things started out, there were no computers, were no digital computers. So you couldn't do the math. You had to do it with analog components. In the analog area, the math could not be computed directly. Computers didn't exist. And later on, computers did exist, but they weren't powerful enough until about the 1980s to do the math behind demodulation, modulation, etc. Okay, and so I want to mention as well two big disadvantages of analog radio. We all own, I'm sure all of us owned or have owned an analog radio. The first disadvantage is that radio is built using analog components. They are subject to the accuracy of the components, right? And so if you have a 47K resistor, right, will a 47,000 ohm resistor, will that resistor be 47,000? Very, very expensive if you find one that is. And they have a tolerance. They'll be plus or minus 10%, plus or minus 5%, right, within these values. And so all the analog components, whether it's capacitors or resistors or transistors or inductors in that radio, the performance of the radio is subject to the accuracy of all of these components hooked together, right? Remember we said analog radio is an approximation of the math, right? And so the radio will work, but its performance will be based on the age of the components, the ambient temperature, that kind of thing. And so the radio will work. It will work pretty well. They've certainly worked. They continue to work today and everything. But if you want things to be much more precise, now that we have digital capability of doing digital signal processing, digital radio, you can make them 10 times, 100 times, 1,000 times. The performance will be 10, 100,000 times better if now that we can finally do the mathematics directly. And so that's a disadvantage of analog radio, right? The accuracy is based on the analog, the tolerance, the accuracy of those components. The second thing is an analog radio is built for a single purpose. Go back 10 years, 20 years, you buy a television. Television is made maybe 20 or 30 years. Even a desktop radio, it's a desktop radio, it has AM, FM band. That is what it does. It's analog components, right? It can only perform the functions for which it was originally designed. That is not the case with digital radio, because we've just seen in these examples, I can use GNU radio and an RTL dongle, right? A little SDR transceiver, and I can have a digital receiver. I can have a digital receiver, digital transmitter, SSB receiver, cell site, radar transmitter. You can use the same hardware for thousands and thousands, any kind of radio, just by changing the software. And rather than being built for a single purpose, a digital radio its performance, what it does depends on the software that gets loaded into the radio, right? And so DSP implements radio systems precisely. And I thought a good way to show that is on the left. See how it's out of focus. Analog circuitry approximates a radio. DSP is much more accurate. You can put things right in focus, because when you're doing the math is very, very precise. You don't have issues of tolerance or anything. So the next couple of slides, if we have a combination resistors, capacitors, and an op amp, right, it represents radio function perfectly, right? The math is implemented on the you approximate that using resistors, capacitors, and active components, right? If you do the math on a computer, you can make it orders of magnitude 10, 100,000, 10,000, 100,000 times more accurate, right? And it's reconfigurable, because you just have to change the software, change the flow graph to get the radio to operate differently. I want to point out, I'm not a mathematician. I have you don't have to be able to figure all this stuff out. There are tutorials, there are resources on the net, and but I'm honest, you have to be willing to read and think. You have to be willing to study the subject on the digital side, a little bit, or depending on what you want to do, maybe a little bit more, right? But you can get up and running with this very quickly. You just have to know a little bit about sample rates and how the digital blocks differ. A digital low pass filter differs from an analog low pass filter. And so I started in this area with no knowledge. I just had an interest. I didn't have any knowledge about GNU radio, no knowledge about signal processing. I just thought, boy, this is really interesting. I'd like to learn something about this. About 5 years ago, probably 5 or 6 years ago. And I started down the road, and I did a lot of reading, and then I got into it more and everything, and it's been really fascinating. It's right up to date. And moving back to the first part of the presentation, if amateur radio operators, you as a ham, you get right up on this technology, you understand how it works, then that increases the possibility that you're going to be able to innovate, right, and contribute something back to the radio art, because nobody's designing analog radios anymore, right? Nobody's designing, it's much like solid state power amplifiers, right? Nobody's designing on HF vacuum tube based amplifiers or anything anymore. It's way more efficient. Do it using digital components. So don't count yourself out because I don't know much about math. If you have high school math and you have the ability to, some time to read, ability to, you're willing to put the time in, you can understand this. Okay, so I got to speed up a little bit because we're getting sort of towards the end. Radio signals are analog, of course, when they're on the air. So you can't transmit a digital signal. You have to transmit an analog signal because electromagnetic waves are analog. And so that is why you need the RTL SDR. You need the software defined radio. You need a bit of hardware at the front end of your system, because in order to receive signals, or in order to take a digital signal and transmit it, you have to convert it to an electromagnetic wave. And so on the air, signals are always analog. There are two converters called the analog to digital converter, the digital to analog converter, that take your digital signals, from your flow graph, and they translate them to an analog signal that can be transmitted over the air. Here's some examples. RTL, they're generally called RTL dongles, USB interface. The three on the top right are from a very cheap one, probably $10 up at the top, to the new elec at the bottom. I think it's about $40, $50. But these are perfect. If you have $20, $30 to spend, you can get started. These are receivers only, right? The two units on the bottom, a USRP and this is the Pluto that I was talking about. The Pluto is about $100, $150. The USRP is more expensive, but they are transceivers, and they are of interest because not only one, and I would say you want to get competent at building a receiver and be able to build a receiver that works before you try to build a transmitter, because again, you want to be able to hear stations before you work them and that kind of thing. But and so radio choices, there's dongles on the left. There are actually three different stages. There's an RTL dongle. I show a new elec. They're a fairly good brand, right? They're $20, $30. A Hack RF is a transceiver. It's about $300. And the EDIS models are more expensive. They're laboratory grade. They have higher quality digital converters and that kind of thing in them. And so they are more expensive. You don't need that. The way to start is to go on eBay, go to Amazon, go to some of the references that I see, and get a mid-price RTL dongle with a USB interface. Okay, foundation, we can skip over this. You can read this later, but digital radio is based on sampling. Signals are sampled in real time. And so the key thing to remember is that any signal that is on the air can be it can be sampled and represented in terms of sine waves, basic sinusoidal radio waves, okay? Two sine waves can be used to represent any form of modulation, AM, FM, single sideband, double sideband, PSK, RTTY signals, all the, frequency shift keying, phase shift keying, that kind of thing can all be represented, or it can all be created, demodulated, or modulated through the use of sampling. Modulation, demodulation is just math. There's an area of math called complex mathematics that you have to learn just a little bit about. And this is where this terminology called IQ comes from. If you read a story on digital radio, at some point they're going to say, yes, they're IQ signals. What IQ is just a representation. It's a sampled representation of a signal that is received off the air, a signal that is being modulated for transmission. You have to take that digital signal, you can use IQ to convert it to that's called a complex data stream, a stream of numbers, right? And so the and GNU radio, digital radio packages, they operate mathematically on these numbers inside the flow graph, right? But when it comes time where the rubber hits the road, you have to transmit the signal or you want to receive the signal, right? You have to be able to convert it from an electromagnetic wave to or from digital form, okay? So the stream of IQ samples, and the stream of IQ sample, that's where sample rate comes in, because the sample rate, the number of samples per second, determines the bandwidth, determines how much radio spectrum you're able to listen to at once. If you want to listen to an AM signal, there you need a certain bandwidth. You want to listen to an FM signal, you need wider bandwidth. And this goes back to the specifications of bandwidth, like bandwidth limitations that we cover in the basic certification course, right? So you can recover the original data from the IQ stream, or you can take an IQ stream, convert it to an EM signal that goes to the antenna that gets transmitted. And so the number of samples per second determines the bandwidth of the received signal. And this is a little bit of the reading that you have to do. How are signals detected? And I'd refer everybody to the Communicator. There's an article. I have an article in the current issue of the Communicator talking about introduction to digital radio. And so this is a repeat of some of the stuff that's in there. We'll gloss over it from now. But again, IQ can represent any form of modulation, right? So you can have AM modulation, frequency modulation, right? And this is called a phasor diagram, and the article will explain that. So I would say go to the article, read about that, gives you a good introduction to how all this, little bit about the math and how these IQ signals work. So transmission from the IQ stream to a electromagnetic signal happens in similar manner. You have to take a digital signal and convert it to analog. So it goes through the digital to analog converter. And IQ can represent any form of modulation. So, in fact, people have developed a cell site, a cellular telephone site, flow graph that runs in GNU radio. You fire up this flow graph and then turn on your phone, you'll see, hey, there's a new cell provider here, right? And so it's just amazing, right? Just amazing. And that would be that uses a USRP, right? So GNU radio can do all of this. It's open source, it's multi-platform, and it is free. Here are a couple of examples of things that have been written on top of GNU radio. First one is called a GQRX. It's a GNU radio-based general coverage receiver. It works with, on the right, it works with any number of devices, an RTL, SDR, RF space, EDIS, any sort of device. That's a subset of the devices that GQRX supports, but it receives AM and FM and single sideband and I think digital modes and several digital modes, that kind of thing. It's a free application that you can download from the URL at the bottom right of the screen. And it's by a guy named Alexander, and he's a ham in OZ9. I think that's somewhere in Europe. I'm sorry, I don't remember where OZ9 is from. But in any case, GQRX is built on top of GNU radio. Another really, really interesting project that was undertaken in 2014 using GNU radio was this ISEE-3 reboot project. This satellite, it's a defunct satellite that had gone silent. It was a solar research satellite that was about, I think, 34 or 35 years old. It had gone dead, and then somebody noticed, some people monitor satellites, and they said, hey, the satellite's come back to life. And so the problem is the satellite came back to life, but there was no way to decode the telemetry on the satellite, no way to command the satellite, because all the equipment had been retired and recycled. All the scientists who had worked on it in the 1970s had retired. I think they found a couple of them, brought them back, and they were able to. They tried to remember what the modulation, demodulation, what the data rate, and all that kind of thing on the satellite was. They didn't have any equipment, so what some keen GNU radio users did is they said, hey, well, tell us how this works. Tell us what the modulation was like. There was a little bit of documentation. They developed a receiver using GNU radio. And in fact, they developed a transmitter using GNU radio, using the proper protocols. And they were able to reestablish communication with this satellite that had been thought to be, would have been dead for many, many decades. And so it's a really, really interesting story. If you go to this jmalsbury.com, it talks about, and also the second reference at edis.com. Edis is the company that makes USRP radios. it's a very interesting story about how they reestablished communication with the satellite. They were able to get telemetry on battery level and propellant level and satellite condition and that kind of thing. And what they tried to do, it was in a sort of a parking orbit, and they said, hey, we're gonna reactivate the engines. We're gonna try to put the thing into a more stable orbit, and then it can continue some sort of a mission. They weren't successful, unfortunately, because the propellant, although the propellant levels were high, there was some leak that had developed in the propellant system over the 36-year hiatus when the satellite had been thought lost. But it was a really interesting project. And the guy on the left actually came to the GNU radio conference and did a presentation about all the stuff that they did. And he works for a technology company and everything. The guy developed they developed very complex programs for that, but it's a very interesting story. It just shows how GNU Radio is so versatile. Resources, if you want to learn more. If this says, and please, I don't want anybody to be scared off. This is too complex. I can't understand this. This is, you definitely can do it if you put in the time to learn the digital side of what you need to know. And start small. I'll give you, start small and do things, and experiment and expect to fail a lot and everything. But and what this will do, this will enhance amateur. It'll support technologists within amateur radio. It'll also support amateur radio's ability to contribute to academia industry and the radio art, radio technology as a whole. So if you want to learn more, you have to learn a little bit about the math behind digital signal processing. This will help you build flow graphs that work more easily. When you first start out, things are not going to work. It's gonna take a long time, but eventually when they work, you'll say, hey, I'm getting it, right? And then the next time, of course, is going to be easier. If you're a ham, you have the requisite basic math, just decide to learn. Don't give up, right? It took me a couple of years to get things actually working, right? To be able to write something that actually works. I didn't understand sampling rate and interpolation and decimation and stuff, but I'll just give you the resources, things that'll help you work. So GNU Radio hides most of the math in its 200 plus processing blocks. So GNU Radio, go to GNUradio.org. You can download, install their frequently asked questions. There are tutorials, but even there, expect to do some background reading. GNU Radio, it's built by a bunch of, largely academics and scientists and people who work in the industry. But I would say, on the other hand, I went to the GNU Radio conference in Arizona. I've been there 4 times, but the last one was in Arizona, and probably 40% of the audience, 40% of the attendees, they have like 300 people, 400 people go to the conference. About 40% of them are hams, people like you, people like me, right? And so there are a number of hams that have taken the plunge and say, hey, I can understand this. This is really fun. I can do some really interesting experiments. And so expect to do some background reading, but go to GNU Radio. That'll help you download and install. And also ask me questions, send me emails if you want to get started. There's a free book. It's called The Scientist and Engineer's Guide to Digital Signal Processing. There is a hard copy available, but it's available for free online, absolutely free. You can download the whole book or download it by chapters. Start at the beginning. It's about digital signal processing in general. It's not really about radio, but that's a positive point because DSP is used in many different fields. It's used in sonar. It's used in mining. It's used in earthquake detection. It's used in heart monitors and that kind of thing. Like electrocardiograms and things. And so the book is about digital signal processing in general. So it's actually better than a book that just talks about radio. And it's really readable. It's written for the person with average knowledge like we all have with and everything. I like the book so much that I bought a hard copy, and I still refer to it probably, at this rate, a couple of times a year. I don't remember something about filters, so I go back and look in the book. It's excellent, and it's absolutely free. Download it if you like it. You can buy a hard copy. They're great. Here's some great videos. GreatScottGadgets.com. They make the transceiver called the Hack RF. And the guy has about 30 tutorials at that URL up at the top. Starts basic and talks about all the things that you need to know, sampling rate and that kind of stuff. And so work through those tutorials. The guy's really good. He's good on email with questions. He comes to GNU Radio Conference as well. If you go to rtlsdr.com, they have all sorts of tutorials and interesting applications. Tutorial, creating an FM receiver with GNU radio. That is the initial, that's the best initial project for all of you, right? If you say, I'm going to learn this, hey, build an FM broadcast receiver, because they're fairly easy to build, and it's fairly easy to build, and you actually get something, right? You get something when you're done, because you have an FM broadcast receiver that runs on your computer, right? Runs on the computer, and you don't have to burn your fingers soldering. Now, there's a very good, when you get into IQ, the IQ, this is the complex data stream, how signals are represented. There's a really good YouTube video on that by W2AEW. I would leave that until you've read about the broadcast receiver and done from the Great Scott Gadgets, looked at those tutorials. But that he really explains IQ modulation, IQ signals very, very well. And so we're coming right to the end. I would say that's a short talk on a really big subject. It's been a brief introduction to technology, and I really think it's arguably the biggest thing that has happened to radio in the past 50 years, right? This ability to define radios in software and improve their performance by defining them in software, and have them reconfigurable by just reloading software, modifying the flow graph, is the biggest thing that's happened in radio. And analog radio, it is not dead, of course, because there are legacy receivers, legacy systems out there, and all radio is analog in terms of the signals, the signals in transit between antennas and everything. But anyway, so it's a big subject, but it's only a short talk. What I hope there is that people know a little bit more about digital radio and GNU radio, and decide to learn more about it. And I would say there is a learning curve, but the outcome is worth the personal effort. I have learned so much through this over the last 5 years, and I think even if you say, I'm going to start now and I'm going to learn a little bit, do some reading, in 6 months you'll know so much more about it. You'll be a more well-rounded ham. You'll understand industry. You'll understand what's happening with all this technology and everything more than you do now. And so that can only be good for the future of ham radio, and only be good for you personally as well. DSP, digital signal processing, software-defined radios, SDRs, they're here to stay. So it's important for every ham to learn at least a bit about them. And that's hopefully you know a little bit more with that, because of this presentation than you did before. And with that, I think I'm open to take a couple of questions if we have time.